It's a product of two trees. I want to thank the organizers for having me here. So today I want to talk about some quasi-isometry rigidity of Bernoulli IID point process in product of two trees. And it's based on joint work with Zhiqiang and Ranfeng. So Ranfeng is a PhD student at Peking University with Zhiqiang, and Zhiqiang did his PhD here with Mario. So let me first set the notation for quasi-isometry. So you notice it's a very well-known. So let's take two metric spaces, and then we consider a map from x to y, and then we say f is a say kappa c qi embedding. If so, you just require that the image, the distance of the image, so for any 2 points in X, so you want it to be controlled by this affine function, so given by kappa is the multiplicative constant, and C is the additive constant. So this is well-known, kind of a standard definition. And then if in addition, this image, so this if in addition there is another constant such that the C prime neighborhood of the image is all of y, then we say F is a quasi-isometry. It's like a quasi-isometry equivalence. So the first line is just an embedding, and if it's almost onto, then you say it's a QI. Okay. So we are interested to study kind of QI properties of quasi-isometries of some point process in space. So just maybe give you the slide theorem first. So it's kind of a very remarkable, maybe let's just say the setting we have is you consider some metric space, maybe metric measure space, and then you take some point process. On this space, you kind of you do not want to consider two arbitrary processes. Maybe you want them to be invariant in law and some other restrictions. And then you can ask, for instance, what are quasi-isometries of this point process? And here I just take the induced metric. You can consider other more intrinsic metric with respect to the process itself, but let's consider the induced metric first. And then you can ask what are the self-QIs. And then another question you can ask is if you take two independent instances, so you just take two independent samples, are they QI equivalent? So give some motivations why these kind of questions are interesting. But for when you take x to be just z, equipped with the usual distance, and take IID Bernoulli 1/2 points, then there is this remarkable theorem of Basu and Sly that was back in around 2012. So they tell you the following. So let's first take just z, and then you do IID Bernoulli points. So this is like you take z, and then you just do this site percolation with IID Bernoulli 1/2. So we equip it with induced distance. So you just have these points, and then so they tell you that if you take two independent copies, then almost surely there exists a Lipschitz map, like a Lipschitz embedding. You don't even need the additive error, so you really can find a Lipschitz map.
Maybe by Lipschitz?
I think the theorem just says Lipschitz. They didn't. I think by Lipschitz is probably too much to ask, right, Tom?
Well, if it's a quasi-isometric.
I think this is the theorem they say. So it's a. I don't think you can make it by Lipschitz. So you kind of yeah. So they just say you have a Lipschitz embedding, but you do not. They didn't kind of. Stack a point on each other. It's really an honest Lipschitz embedding. So you have kind of one. You can embed one copy into the other. And then they also show an analogous statement for R. So for R, on R, you can take 2 copies of Poisson. So you take Poisson. Independently. I think you can even change your intensity. And then they show that there exists a QI. So the conclusion they say is that these 2 processes are quasi-isometric. So these are the 2 theorems as they state.
Sorry, is there condition on the intensity?
I think they can change the intensity here because both of these processes are translation invariant. So these are constant Poisson, like the standard constant intensity. Okay. So this is quite remarkable if you think about it. Kind of you have these random points and you can kind of match them up on all scales in this manner. And the proof was quite involved. That they did this careful multi-scale analysis to prove existence of such points, such maps. And then later in joint work of Basuslai and Sidorovicius, they extend the first statement to higher dimensions. So we're interested, and then this type of question, you take 2 kind of independent point processes. Are they quasi-isometric? The question was sometimes attributed to Miklos Abert. He specifically asked the question. So if you take kind of you change your kind of base space, what kind of situation you expect? So he conjectured that if you take Poisson points on R, then you do get QI like this. And if you do it on some rigid space, for instance, the symmetric space of SL3R, then you expect non-quasi-isometric. So this is the kind of conjecture. And that's what we want to explore here. So we want to consider kind of a rigid situation. So you take some higher rank symmetric space and then see if you can inherit some QI rigidity there. So that's what we want to do. And maybe say some motivation for that side. So since I can think more about groups and dynamics, so there's some kind of not very mature, but I'll just say some motivations. So there is this idea of studying kind of. So you kind of want to find probabilistic analogs of kind of discrete subgroups in a symmetric space, so in Lie groups. Because the kind of the study of discrete subgroups in Lie group has a very long history, and they're important for many reasons. And there is this kind of a philosophy that sometimes you can simulate some properties of discrete subgroups by point processes. So it's a little bit like you have some objects that are kind of hard and maybe have some number theory difficulties, and you replace them by some probabilistic points, and then you hope to gain some insight from studying these. And there is already a very successful story with Poisson point processes and lattices. So there is this. First, if you take G to be you just think of a Lie group or some locally compact group. Maybe just take it to be, say, SL3R or SLNR. Some locally compact group. And then if you take a lattice in G and think of where the points are, so it comes with the symmetric space where you know very well the geometry. And then when you take a lattice, you can look at where the lattice points are on the symmetric space. And you can also make use of the fundamental domain. So you have this G mod gamma, which you can equip it with normalized Haar measure. So this is the G invariant measure. So you can normalize it to be total volume 1, just because it's a lattice. That's by definition, you can have that. And then you can think of this as your probability space and sample a point from there. It's like coset representative. Then this way you have, once you have a kind of a coset representative here, with sampled according to the invariant measure, you can project to the symmetric space and think of them as some kind of random point process. There is a probability measure here. You do have this random translate of your lattice point, and you can study its properties. And at this.
Just a question, just to be clear. So the quasi-isometric embedding, it doesn't have to be 1-to-1, right?
Yeah, so defined like this, you don't have to. You are allowed a additive constant.
Right, and doesn't have to be onto because you.
Yeah, you also can allow yourself. Yeah, you don't. Even if you ask for QI equivalence, you have this other constant so that you can. Yeah, you can.
So is it obvious that if you have a quasi-isometry from pi 1 to pi 2, you also have one the other direction?
If you have a QI like almost onto, then you can take it. There is an inverse that does similar things, but you might need to change your constants a little bit. So it does admit, it does admit coarse inverse.
Okay, so with a little work, you can see that.
Right.
If you have one way, you have one the other.
Yeah. But just an embedding, of course, you cannot invert it.
Right. Sure. Okay. And so that makes this question of whether two Poisson processes are quasi-isometric, that makes sense to say.
Right, exactly, yeah. And right, so kind of this is a way to think of lattice as kind of a point process on the symmetric space. And so typical examples of lattice, for instance, in SLNR, maybe the most familiar one is that you take a Z as coefficients here. And these are actually very difficult. If you think about the points, they have some arithmetic nature. It's actually very difficult to understand where they are and so on. So, but on the other hand, if you consider Poisson point processes, then there is no difficulty in points counting. You know very well the concentration and everything. And so you can also, so just saying that you can also consider, for instance, a Poisson point process. So here I always mean constant intensity with respect to the Haar measure on X. Then you can kind of think about, do they admit some similarities? What you can, if you understand very well some aspects for the random points, can you transfer information back to lattice? And recently, people started to look at kind of from measure equivalence point of view to study the point processes. There is this notion of cost, and in work of Abert and Melik, they initiated the study of cost of Poisson point processes on locally compact spaces, and they have this. It has this interesting property that it kind of Poisson points attain some maximum for a family of possible actions. And based on this, in the recent breakthrough of Frajic, Melik, and Wilkins, they solved the fixed price 1 conjecture for higher rank lattices using Poisson points. So this kind of motivates people to think more about the. So it's not. So there are already kind of breakthrough results, kind of using the Poisson points to go back to more classical object kits, and it's really very promising and encourages people to think more about this. So here we're going to focus on the QI aspects. So maybe I just tell you what we have for, and it will be clearer later why a product of two trees is a reasonable model to consider. So we see here that if you take Z or R, you can find these quite sophisticated quasi-isometries based on multi-scale analysis. But if you go to kind of a rank 2 space, like a product of two trees, then have the following rigidity. So let's maybe just do this. The setting is that we just here T is just a regular tree. So regular Q plus 1 tree. So you have Q degree Q everywhere, Q plus 1 everywhere. And then we just take the point process is just Bernoulli. So for us, it doesn't really matter what P is, since we're only going to consider induced metric. So here, what P is doesn't really matter. So just take IID by Bernoulli point process. And then, so we can consider the following. So we're just going to consider self-QIs given a sample, and whether two independent copies are QI or not. So the statement is the following. So this is the main theorem. We hope to post it in the coming weeks. It's almost complete. So it says that, we fix these multiplicative and additive constants. So given this kappa and C, so these are given, there exists another multiplicative constant that only depends on these. So this is just depending on the parameters given constant, and then there is this map. So it's going to be the additive error. So it goes from, it's basically goes from the points. So maybe I just call the space, I didn't save the space. Okay, so this is the set, and then you maybe take another point. So there is going to be this radius. This is a random variable, which is invariant under the automorphism. It just means that if you if you take an automorphism of the space and act, so this just means that if you act on both the set and the point diagonally by an automorphism, then it doesn't change the map. And this is a measurable map. I didn't say that. So this is going to be the error term. Maybe I keep this statement. Such that any QI embedding, so you consider a QI embedding with the prescribed constants from the point process to yourself, satisfy that it's actually just wobbling. So you have the distance between your image and itself is just bounded by this constant times. I guess I don't, in this formulation, I don't even need to introduce this lambda, but it came from other reasons. So this is almost sure. So for almost every sample, any of the QI embeddings, it's actually just local wobbling. You cannot move it any. So this is random. So here, this R, it's really in this formulation because the map is only defined on the points. So you can as well as set x. When x is not in the points, you just set it to be 0 because it just doesn't affect the statement. So this is really kind of some radius that is based on the environment that you see. So it's like you look at this pair, and it's only kind of non-trivial when x is in the space in the set of points, and then you look at this environment. It's going to give you a radius. And the statement says that any QI embedding of this set of points into itself is kind of local wobbling with this within this radius. And this radius, it's kind of a random variable, and the law is invariant just because of this. So you just get this invariant field of radius, and kind of depends on the environment seen from this point. And it's going to kind of restrict how your QI can move. And there is no global kind of embedding, non-trivial embedding. It's only local wobbling. So that's the statement. And then there is by similar methods, you can show that, let me just say it's 0, 2.
So can I quickly ask you, do you think of your tree as actually just a set of vertices, right?
Yes, so there is this graph metric.
But I mean the picture you drew, that looks like the tree how I think of it, that the edges are part of it.
There are no edges, right?
For you,
Yeah, it's just the points.
Just a
Just the
discrete
points.
set.
Just a
And
discrete.
it carries the graph metric, but it's,
Right, exactly, yeah. So you carry a graph metric and then just restrict to this point. Yeah. Any other questions? So and then for kind of the similar mechanism will give you that if you take two independent point processes, they are not. There is no QI embedding from the first sample to the second. It's actually easier to prove this statement than the first one because you have more independence in the second statement. When you consider self-QI, you translate it to a different place, then you gain independence. So it's actually easier to figure out this. But they follow from the same reason why such a statement can be derived. So maybe just explain a bit what is the...
Sorry, did you say what happens for one tree?
Oh, yeah, so I didn't say because I'm not completely sure what is known. There is this, it's announced in some talk by Athreya and Chochi, so maybe I should write it somewhere. So, but since I haven't seen the paper, I do not exactly know what they prove. I also hope I didn't misspell. So they prove that if you take two Gaussian-Wilson trees with some restriction on the offspring distribution, then you would have quasi-isometry equivalence between two independent Gaussian-Wilson trees. So it shows you that for Z or R or this one tree, you do have a sophisticated way to match up your points. So what we state here is it's kind of a pure rank 2 phenomenon that you take two flexible objects and simply by rank 2 you gain some rigidity. So it's expected that if you replace say X by some other higher rank objects, for instance the symmetric space of SL3R, then it's going to be even more rigid. So you expect this kind of a phenomenon to be true on even more rigid objects. Maybe I say a bit in comparison what happens for kind of lattices. So the proof of this kind of QI rigidity, it follows the same kind of traditions. It all goes back to Mostow rigidity. So the idea is that if you want to study some properties of lattice or similar objects, you always want to push your map to the boundary. So here, for instance, you start with the QI embedding, then you do what you can to induce a boundary map, and then you study the properties of the boundary map, you gain something there, and then you pull it back to your space. So this is the kind of the format, and it is a very long list of theorems kind of inspired by Mostow rigidity and kind of extend to a lot of different settings. So here I should mention some historic background. So this relevant, we say, important generalization or extension of Mostow rigidity is this Sullivan-Tukia theorem. So the original formulation talks about kind of uniformization of quasi-conformal maps, but it also immediately gives you QI rigidity. So if you have, say, some finitely generated gamma that is QI to a hyperbolic space, then gamma, let me write a big Q. Then gamma is virtually a co-compact lattice there. And so I mentioned this because it's also very natural to ask the same question for Poisson point processes on Hn, and it's maybe more natural than thinking about rank 2 spaces, because there you do have this QI rigidity, but it's more flexible than in higher rank case. This is it's a very natural question. What happens to Poisson points in H3? Does it kind of, what can you gain from understanding of the quasi-conformal uniformization there? It's a very natural question. I hope Ranfeng can continue to work on this for his next project.
So sorry, I mean, so gamma is a group, right? Or...
Yeah. So here these are for groups. Yeah. So these are kind of situations for lattices. So here is gamma is a finitely generated group. So I'm trying to kind of explain some historic background. So this QI rigidity has been studied a lot for lattices. So it's actually a complete program to classify QI, kind of what groups are QI to lattices in Lie groups. And there is this Sullivan-Tukia theorem. And then...
Sorry to interrupt again. So what did you say now about the Poisson point process? I mean,
it's an open problem, and I think it's very interesting.
What is the possible statement? What's the conjecture? What's the problem? Precisely.
I would think this statement is true. However, you might have some interesting things coming in the... Yeah, it's not obvious because this situation is more flexible than higher rank. Yeah, but I do believe that you can still have a non-QI equivalence between independent points. And so maybe I skip the some stuff in between. And then there is this theorem of Kleiner-Lieb. They tell you basically what happens in higher rank symmetric spaces. So you replace Hm by higher rank symmetric spaces. And they tell you kind of quasi-isometries for irreducible cases. You will be kind of within bounded distance to isometry. So it's more rigid than this case. And then, so for this type of, for point processes, the most kind of, they're somewhat closer to non-co-compact lattices, so the kind of non-uniform lattices. So for non-uniform lattices, there is this result of Schwartz in rank 1. But we always need to rule out this H2, which is flexible. And then in higher rank, there is this work of Zhiqiang that solves the question was asked in Schwartz. He conjectured that if you take a non-uniform lattice in higher rank, then the QI, self-QIs should just be the commensurators of the lattice. And it was solved by Zhiqiang completely. So this is kind of a higher rank. So I'm not going to state very precisely all these known results. So here, kind of these point processes, they locally look a bit similar to these non-uniform lattices, but you can see the difference. So for higher rank lattices, their self-QIs are really just given by kind of the commensurators of these. So for instance, maybe just say QI of higher rank non-uniform lattice, it's really given by commensurators of the. So for instance, here for SL3Z, the commensurator is basically SL3Q. So you have these kind of arithmetic things going on. And so if you think about where the points are, so for non-uniform lattices, inside the space, you see holes in between points, but they come from like boundary horospheres. Kind of these holes are created by horoballs. There is like a very specific structure at infinity, and it's actually important for Schwartz proof that he really proved this pattern rigidity at infinity, that you have to move cusps to cusps and so on. And for these points, for point processes like this, you actually the holes are created by local irregularities. So you don't have these global commensurator, but somehow you do have these local irregularities that allow you to wobble a little bit. And it's not hard to convince yourself that you do have these locally kind of a strange. For instance, you have a big region, only 2 points. Then you're allowed to swap the 2. So this local wobbling is allowed by kind of irregularities in the random points, but you do not have this global structure that there's no commensurator or things like that to globally move your points around. So that's explains the difference between the statements. But the proof of this kind of follows the outline of the strategy of Zhiqiang to prove QI rigidity for non-uniform lattices. So it starts with this quasi-flat. Let me see how much time. I explain in the remaining 10 minutes or so, try to outline the sketch how you go about these kind of statements. So the idea is to induce a boundary map. And then you prove some properties of the boundary map. That's always the method to go. And here, the important thing is that there is this theorem telling you what happens when you try to embed Z square into a symmetric space, into a space like this. So you consider a kind of QI embedding of this. You will want to know where kind of one flat goes. And here you see that it's the rank 2 exactly because in one tree you only have these thin geodesics. When you take a product, you have these copies of Z square embedded, and these are the maximal rank, like the 2 is the maximal dimension you can get inside this space. So that's why it's a kind of a rank 2 situation. And so there is this theorem called quasi-flat with holes theorem. It's sometimes also called embedding a Swiss cheese or something like that. So it's there's a version for symmetric spaces by Zhiqiang and Fab. That was actually before Zhiqiang's results. The paper on non-uniform lattices, he used it as the kind of the first step, it's the beginning step of his proof. And there is since we took a product of two trees, it's not exactly a symmetric space for Lie group. So there's work of Wortmann later generalized Zhiqiang Fab to reductive spaces and buildings and so on. So the thing we need is coming from Wortmann. So what it says is that if you have a kind of a regular enough set in Z square, you want to embed it into a structure like this, then the image is covered by boundedly many flats. So your image of a flat cannot go crazy. It's at most kind of go into boundedly many flats. And
so flats in the product are essentially the products of geodesics, right?
Yeah. So here flat in it's just you have like one geodesic and another geodesic is like is of this form. Yeah, it's just the usual picture, and you have kind of four chambers. So, but we don't really need the language. So here, I just want to explain that this is quite a flexible theorem. So it basically tells you the following: the kind of regularity you need is the following, and it will also explain where this kind of R comes from. So given a set, and say given some constants, then you can define the following kind of regular points. So these are those points that it becomes kind of regular in the following sense. So you allow yourself this row distance to be kind of, you don't really care what happens within this distance. And then you take a point outside and you ask yourself how many U points are in this ball around Y with a radius epsilon times this distance. It's kind of a graded notion. So this it says that for any Y that is not in this small ball, you look at this ball around Y with epsilon times the distance. This is a kind of this proportional to the distance to x, and then you count the number of points, and you want this to be kind of bigger than 1 minus epsilon. So you want this to be kind of quite full. And the quasi-flat theorem tells you that for any, if you take an embedding, so this theorem tells you that if you take an embedding into X, for instance, say is a QI embedding with kappa and C, then there exists some constant M that only depends on kappa, and then some other kind of constant that depends on epsilon, so for sufficiently small epsilon. And then some additive constant that depends on all the previous constants, such that the image of these regular points is within kind of the neighborhood of M flats with this additive constant. So this is kind of the starting point for inducing a boundary map, that you have this theorem that tells you that the image of kind of these relatively regular points they have to be near a finite collection of flats. And there are kind of these nice examples that shows you that you can indeed embed one copy of this square into, say, 3 flats. That's totally possible. So this is kind of only talks about 1 flat. And to start the proof, you take your percolation points, and then you do this usual kind of a coarse-grained picture to take this kind of to fatten it up so that your point has a very high, like close to 1 density. And here there's no subtlety because we only count the points. We use induced metric, so there's nothing subtle there. So you, and then after you fatten up the points, you can see that you always have kind of satisfy this kind of condition in in these flats. And then this delta, it comes into this additive error because you do have some local flexibility, and this constant from this quasi-flat theorem will come into this R. And if you track down the constant carefully, I think we believe that as a random variable, this should have tail bounded by exponential decay. So it's actually quite a tight family. And then, so this is the beginning of the proof. So you use kind of verify that we do satisfy this kind of regularity and can see that the flats, at least these regular parts, are mapped into boundedly many flats. And then the second step, so this is step 1. And the second step is to use transverse flat configuration. So this is also down in Eshkin's original proof. So basically, if you consider 1 flat, it can go to several flats in the target space. But if you think about kind of a transverse configurations, so it's like you consider 2 flats sharing a line, for instance, these are like 2 flats intersecting on a line. Then if you look at where both of them go, and after some argument is quite involved, you can figure out by geometric arguments that the intersection, this hyperplane, has to go to 1 hyperplane. So this transverse flats, you show that hyperplane here is just a line. So this kind of hyperplane must go to a hyperplane. This is quite involved geometrically. It took us some time to understand what Eshkin did and how this works in the current situation. But in the end, you can show that it's not possible for 2 transverse flats to behave in a strange way. It just doesn't work. And after this, then we can obtain a boundary map. So you obtain. So after this step, what it gives you is that if you start with this embedding, so back to this. So here we do not need to consider where it goes back to itself or something else. It just you take a embedding. Then it induces a well-defined boundary map. So it goes from the boundary of 2 trees. So these are product of Cantor set to product of Cantor set. So it basically tells you a chamber here. So here the boundary of a tree, we think of it as half geodesic ray.
Do you really mean product of 2 Cantor sets or the join of 2 Cantor sets?
I mean the product I want to. So this is the Furstenberg boundary to Furstenberg boundary. So chamber to chamber map. And you also have, it's actually a better statement that this line to line kind of, you also, maybe I finished the sentence and you think it is what you think. So this is kind of traditionally what the people call boundary map. You take a quasi-isometry inside, and then you induce this chamber-to-chamber map on the Furstenberg boundary. And in this current situation, actually the map has to factorize. So this, if you take 2 rays up to a swap, it has to be just, so it factorizes into 2 maps, so you can as well as think of it as defined on the drawing. That's also correct. So the reason for this is because if you just want to argue that this map doesn't depend on the second coordinate, and if you think about what is in the interior, you have these hyperplanes. These are like just the geodesic rays. In the product, you have kind of parallel bounded distance pieces. And if they go to different coordinates in the image, then they will diverge in the image. But however, these are parallel lines in the product, so the distance is bounded in the domain side. So you can just, so the reason this factorizes is not hard. It's just because of the geometry of the trees. And then once you have this boundary map and understand that it factorizes, then we can move back to the space. So that's the last step. Maybe just write it here. So the last step is to move back to space. You can say that, so the way to think of it is that for reasonable points, you think of it as the intersection of 2 flats. So you take not like a transverse like here, but 2 flats that really only touch at 1 point. If you know where each of them go, then you pin down where x goes up to a distance. So that's how we lifted the boundary map back into space, because you know where the flats go. And in the end, it gives you that any quasi-isometry embedding of the set into X, so without specifying where you go, it has to factorize inside as well. So your map you have 2 separate lifts, and it will read you each coordinate and tell you where to go up to an additive error. And then so this phi itself factorizes. And then with this information, you can deduce these 2 statements. It limits what possibilities you can have. Just by Borel-Cantelli, you can enumerate how many possibilities. The factor maps are like, you have way less flexibility than what you had in a priori. And then it's not difficult to deduce these statements from this kind of lift of the boundary map. And that's the sketch of the proof. And I think I'll stop here. Thank you.